John here. Let's have a look-see at the circuit board and how I laid it out for the Z80 Retro board. Alright, this is the 3D viewer in KiCad with some of the parts, like this reset button over here doesn't have a 3D model, so I'm sorry about that. But most of the rest of them do, at least the sockets do for the chips that are on the board. Let's do a little survey of what's going on here. If you follow the channel, you'll notice that I posted a video on how to solder in this connector over here, which is not necessarily the easiest thing I've ever soldered in. As you know, if you've seen it, I had a little trouble heating up this part of the socket over here to get this pin, to get this corner soldered down okay. I may reshoot that with this board because you might notice this board's a little bit different, and that's the point I bring it up. The board that I used was the revision 2 of this design. Up here you can see this is revision 3. 2063, I just assign my projects a number, and I add 1 every time I make a new circuit board design or dabble, even if it's an experiment that I throw away. I just add 1 to the last one. It's just an arbitrary number. The .3 means this is revision number 3 of Project 2063, all right? Just so you know what that means, at least on boards that you might see from me. The board that I showed when I soldered in the SD card a couple of weeks ago was revision 2. So the big difference between revision 2 of the board and revision 3, what drove me to do it, to move on to 3, is this header right here. The revision 2 board did not have jumper number 11, this 6-pin header here. And the reason this header is even there is, as I mentioned when we were looking at the schematic, this allows us to use jumpers to just select whether the SIO chip right here is either directly connected to this oscillator over here, X2, or indirectly connected to it by way of the CTC, okay? So what happens is this runs at a rate that if you put the jumpers in here, well, it depends on the crystal you buy, of course. The crystals that I bought, or the oscillators, I should say, that I bought, run at a rate that's exactly 115,200 bits per second times 16, 1.82 some odd megahertz, all right? That, if you put this jumper in the right place, sets that oscillator output, goes directly to the SIO, so it runs at 115.2, or at least it can. Reason I need this jumper is 2 reasons. The main one was, in case you haven't noticed, there's a chip shortage in the world right now, and I couldn't buy a CTC. No one had any. So in order to make this board work, I had to put little wires in these socket holes and jumper the clock oscillator inputs to the CTC over to the outputs that route the divided output of the timers over to the SIO. And I thought that looked kind of hokey, and it is kind of hokey, and you know, the wires could pop out or something. It's annoying, and I thought to myself, it'd be nice if I just had some headers down here. I could put a jumper on there, and then it doesn't matter. So I could build it without the CTC, and it wouldn't look like a total mess when we get to this part of this series, okay? It turns out the other reason is that the CTC has a minimum division count that it has to have. All right, it's difficult for the CTC to run at a rate that allows the output of the CTC to run the SIO much faster than like 38,400 or something like that. We'll look at the details when we look at the software, okay? Point is, there's another, even if you buy the CTC, you may want to have this header in here in order to run this SIO at speeds that are faster than what the CTC would normally want to be able to generate, okay? Again, that has to do with how you configure the CTC and stuff like that. There's the main reason to move on to version 3 of the board. You know, as all engineers, if you're going to mess with it, you might as well go nuts, okay? So while I was in the neighborhood, I noticed that if I was creative and rearranged parts over here, again, if you looked at the revision 2 board when I soldered in this, I also soldered a voltage regulator over here to generate the 3.3 volts needed for the SD card if you put the SD card on the board. You no longer see that here, okay? By moving that regulator onto the back of the board, okay, which is not needed at all unless you have the SD card. By moving it underneath the SD card, I get it out of view. and it helps the retro vibe. Okay, it doesn't detract from the retro vibe as much as it would with it on the top. Okay, that's a secondary reason or feature for having it underneath the board instead of on the top. The main drive was to get this extra 7432 series chip in here. This chip here is the chip that has the 4 OR gates in it, as you recall in the schematic, that had to do with the bank selection for the SRAM, I should say here, the 0.5 megabyte SRAM. Okay, without this chip, I could only support 4 banks of memory rather than the 16 that I can have with this chip in here. So by finagling around a few things and, eking something a millimeter over here and moving the reset button, as I recall, and rearranging these resistors here, I was able to get one more these 14-pin chips in here to let us get more memory into our design, which, for some reason, I got excited about that while I was playing around, so I put it all in there. Make it happen, all right? So what else do we know about this board? Let's look at this connector over here, the main power connector. As I look at it right now, it's one of those things. Every time you open up a circuit board and look at it, you always think, boy, I should move this via over here somewhere else, or I should add another track here, or I don't like the way this rounded thing is. There's always something to mess with, right? I'm a programmer primarily by trade. I can't open up a program without thinking, boy, I should change the way this function works, or this is not as efficient as it could be, or whatever. All right? So there's always stuff that you didn't notice yesterday that you want to do to it. All right? So my point is, as I look at this thing right now, let's look and see what happens, how the power comes into this board. This is this USB connector. It is a through-hole set of pins. It has these 5 pins that stick through here. This pin right here and this pin over there are the power pins from the USB, okay? Now, when you solder this in, the pin needs to go through these holes. The solder wicks up into the holes, and this particular connector is like a plastic base that runs flush against the circuit board. So what happens is the back of the board over here, if I can get this thing flipped over while we're zoomed in on it, there we go. When you're soldering this in, you get a nice fillet down here, a big, like a cone of solder that develops around this this pad and on the pin, okay? And it'll go down into this hole, and it helps bring conductivity is the whole point. When we look at the layers of the board in a minute, we'll see that the power for this circuit is delivered in an interior layer. This is a 4-layer board, okay? So in order to maximize the surface area and the amount of copper in the conductive materials to get the inner layers connected to the pin here is my whole point, I wanted to make sure I had enough surface area. So if all you had is this one lousy pin, I mean, think about that. You got a copper layer inside this board. It's like the thickness of a piece of paper. And the only thing that connects that piece of paper to this pin is the edge of the paper that's exposed around the inside of this hole. That's not a lot of copper, okay? Yeah, it's enough and it'd probably work, but that's not a lot of copper. So what I did is I put more copper on the surface and put these vias over here. So I have this hole here, I got that hole there, and that hole there. It's 3 times the copper I would have if I didn't put these over here, okay? Now those vias connect to the socket. By the way, if you're inside here, you hit this little magnifying glass, it'll recenter it and zoom it so that it's straight. If you ever get your board into a wonky situation where you can't zoom in the way you want it. You'll notice I added extra copper to connect this is the 5-volt pin to these vias on both the top and the bottom, all right? Now, in my mind, when I looked at this right before I kicked up the old microphone here, I noticed, I happen to know that this pin on this resistor over here is connected to 5 volts as well. So this pin connects up to the inside layer, which then comes over here, which connects to the pin over there, all right? Now, as I explained, I wanted to make sure that I had plenty of surface area to get the power connected to that inside layer. What am I thinking? Why didn't I also add a track along here to take advantage of the fact that there's another hole over there, and it has a lead in it, and it'll be full of solder and everything. And that would add even more area to further improve the ability for the 5-volt power to flow from the pin on the USB connector here into that inside layer by way of this hole, this hole, this hole, and it would be able to go in here as well. And if you zoom out, guess what? This pin is connected to 5 volts, as is this pin here on this diode. So I probably should have taken and put a big fat track, you know, from like this via here to that hole, and then up and around to this pin, and then back in there. And then I would have taken advantage of the mass, the width of that track from this pin through all these holes, all right, to connect to the inner layer. Again, I'm just kind of free associating here on things that I'm noticing about the way I designed this board right now. I have less concern about the ground, by the way, because the ground is also connected to the top layer and it's filled. See, the ground can flow everywhere, and these huge studs here, which mount the case of this USB connector, are also connected to the front layer, the back layer, and the interior ground layer. All right, as are some other vias around the board. Okay, ground is done really well on both the top and bottom of this board. The 5 volts, like I said, I'm only really connecting from the USB jack to the inside plane with only these 3 holes and no other ones. All the current, the entire system has to flow through these three holes in vias. So, you know, whatever. I probably should have just put some more on there, is my point, or hooked up these other pins. I'll probably do that and come out with a reversion 3.1 or something like that, because that really doesn't change the design or the functionality or anything. It only changes the foils over here where the copper would flow, in my opinion, which might improve if you drew a lot of current. I've made this, I've let it run for days and days, and I have no problems whatsoever with it, so I'm sure it's okay. But, you know, like I said, could be a little bit better. Anyway, I'm done free associating on that. Let's look at a few features of this thing. These long things are resistor networks. There's a lot of resistors. These are pulling up on the address bus, the data bus, and the control bus. Also, this one down here pulls up on the inputs. This is the resistor network that is the pull up on the inputs for the general purpose input port. And if we take a look at the schematic right here, that's this resistor network right here, RN3. So it's pulling up on all the, like the printer signals, as well as the SD detector input, and of course the reset switch, right? What else we got going on here? I use all through-hole capacitors. It's annoying that these through-hole capacitors cost like 4 or 5 times as much as the equivalent surface mount capacitors, right? Granted, I'm complaining that I'm paying 10 cents a piece versus like 2 cents a piece or something like that. In the greater realm, it's not that much money, but, you know, on a percentage basis, it's ludicrous, I'm telling you. Yeah, but they get the right retro vibe if you see all those little guys on there. Okay, so the resistor networks and these giant white slugs, all right? I'll give credit where credit's due. This is a Fran Lab thing. If you ever see her channel, she's got some really interesting engineering that she does on that channel. And in one of the videos that she did, she was talking about how when she routes a board and she works on the legend, she puts these big square slugs on her board because, you know, if she's poking around on a circuit and she wants to know where pin 1 is, it's not always obvious after the fact, but when you put the parts in there and stuff like that, where pin 1 really is supposed to be, or even before you put them on, if you're going to be putting the components down. In this particular case, the concern I have are these resistor networks. So there's something I really want to make sure you know. These big white slugs are always next to pin 1 of each of the components. See this slug here? All right. When you get a resistor network, let's see if I can zoom in. Yeah, there you go. In the 3D model, you see the black dot here? There's going to be a marker on these long parts when you buy them that represents where pin 1 is. So when you put them in, you have to make sure, is my point, that pin 1 is on the right end, right? These particular resistor networks, the way they work is there's 8 resistors in here, and each one of them has one pin going out, these 8 pins here, and the other end of the resistor are all connected together in a wire that's inside this case that all goes over here to pin 1. So if you turn around and put this thing in backwards, this circuit will not work. It will fail. You must make sure to put these things in correctly, okay? Now, without the slug, it's not too bad. You can see if we turn off the 3D models, you go in here and you say, don't show me the 3D through-hole models. It'll go away. You can see that if I didn't put the slug there, you'd see this square and the square pin on the board to let you know where pin 1's supposed to go. Same way with these chips and stuff, all right? But as Fran points out, and as I can absolutely agree with her sentiment, and that is once you put a part in here, or even if you just set it on the board and you're about to solder it in, you've covered everything. You can't really tell, did I put it in right or not? Especially when you're debugging a circuit later on. You know, it might be that you did put it in backwards and you've covered all this stuff up and you need to look around and say, boy, do I remember, is this in right? You know, so you want to know, you want to put something on the board so that it's exposed after the fact, as you saw, where pin 1 goes. Now, I really got to emphasize a lot, RN1 here. Notice the pin 1 for RN1 faces down, okay? And pin 1 for this RN4 up here faces up. So when you put these two in here, one of them faces up and the other one faces down. The reason I did that, we'll see when we look at these little traces in the circuit board, is that if I put pin 1 up here, it would require me to route all these signals down in a kind of go down and back up. I needed resistors up here more than I needed them down here, is my point. We'll see that when we look closer at the PC board editor view in a minute. All right. So where are we at then? All the pin 1s for all the socketed parts, the chips, are on the same orientation. They're always facing up. The little dent here says pin 1 goes on this end. You can see the squares and you can see these slugs on here, all right? Try to make that consistent. The pin 1s for these headers here are pretty important as well. When you put a ribbon cable on here, you need to make sure that you put the pin 1 in the right end. I did not buy shrouded connectors. I just put headers in here with pins. And by the shrouds, I mean the big plastic is like a bathtub around it, and that has a guide so you cannot put the cable in backwards, is why you use those. I let you put the cables in backwards because if I put the shrouded connectors on there, they wouldn't fit, all right? Believe it or not, these are as close together as you can possibly put these if you're going to put insulation displacement connectors on them, because the connector housing sticks out over these ends. There's less than maybe a millimeter gap if you put the connector on both the A and B ports here. Once those connectors are in, I don't dare put them any closer together than this, all right? And the gap over here for the printer as well, all right? So if those, think about that, right? If the connectors are so close together that there's like a millimeter gap between the two, if that, okay? When you put them in, where does that giant shroud bathtub thing go, right? The answer is they won't fit. If you put them this close together, this would have to be moved over to the right. Then this would have to move over to the right, and you can clearly see there's not enough PC board room for all that stuff. So that's why I did it the way I did it. And these pin 1 slugs are going to be very important that you look at when you put the cable on here. If there's like sometimes there's like a colored stripe usually on the pin 1, so you can make sure you put those in correctly. All right. So that's what's up with those slugs and the reasoning behind the way I did the board the way I did it. Put the regulator underneath here for looks more than anything else. I may have to re-record that recommendation on how to solder this in, by the way, because when I built my Rev 3 board, what I noticed was if you put the regulator on the back of the board, when you solder it in, all the flux runs down through these holes, all right? And once that happens, if you put the SD card on first, all that flux runs up into the SD card where it's almost impossible to clean. Okay, so the recommendation that I made in the video when I was soldering in the SD card was to try and solder that in first, because if you screw it up, you could just throw the board away. So no one will ever know. Well, that's not a good bit of advice in this scenario because of the flux problem, right? In this scenario, boy, I can't get... You see, now I've got to the point where it's rotating in a weird way. I can always go grab the... Yeah, and I kind of lost it. You grab this and reset it again because I messed up, right? So if I wanted to flip this thing over and then zoom in again... All right, so my point is that if you put together a Rev 3 board, what you want to do is solder the regulator on here. And when I did that, that's when the flux runs down these holes. And you solder in these capacitors, and when you do that, flux runs down these holes over here. Okay? So if you put the regulator and these capacitors on, hit it with, isopropyl alcohol, like 90%. Just go over to whatever, your Walgreens, CVS, whatever, your local drugstore, and buy a rubbing alcohol. It's isopropyl. It's the same stuff. Get a toothbrush and brush this sucker, get all the flux out of there. Flip it over before you put this SD connector on there is the key. All right. Oh boy, I did it again. I'm starting to really like this little fix it button there. Then when it's all cleaned off, you can put this SD connector on here. Okay. Now, if you're careful, you can actually do this using only the flux that's in your in a spool of solder, which would minimize the amount of flux that you put on here. I put some extra stuff down in the last video when I did it on this, which you can definitely do, and you can clean that up. But the less flux you put on here, the easier it's going to be, obviously, to clean it off. So again, I warn you, if you're going to go for this surface mount route, do the regulator on the bottom first, clean everything up before you put this SD connector on, all right? Once the SD's on and the regulator's on, everything else is through hole and it's nowhere near this, you don't have any flux problems, okay? Look at these giant pads here underneath these oscillators. Again, there's a shortage of like everything in the world right now. When I ordered these oscillators, I was concerned I couldn't get the frequencies that I wanted, and I did notice that I could get them in surface mount packages. So I hedged, and I put both the through-hole footprint down as well as a surface mount footprint you can see here. So if you can't buy a metal can oscillator at the frequency you want, look to see if you can get a surface mount one. So you can throw the surface mount down on here. The pinning and stuff is the same. It would work if you had to go that route. Now, the way these are literally stacked on top of each other like this, if you put the metal can on there and solder it indirect, or if you put a socket in here and then put the metal can in the socket, which is what I prefer to do, that fully covers up and obscures these footprints so that you, again, don't lose your retro vibe if you want to go the all-through hole route, okay? What else do we notice this while we're looking around in here? We turn on these parts. I guess the only other thing that I could mention is that when I went from revision 2 to revision 3, remember my motivation was because I couldn't buy my CTC chip. I had to add these resistors up here, R10 and R13. And as we'll see in the schematic, we'll talk about this when we write the software. This is actually to allow us to write software for the board so that the SIO can generate interrupts. We'll find out when there's no CTC in here. The problem was that I needed to be able to propagate the oscillator, as you recall, over to the SIO, and that's why I put this header in here. There's another signal that you also have to concern yourself with, and that is the output of the CTC. It generates a handshaking signal that's used for the interrupt circuit logic, okay? And the CTC tells the SIO when it's okay to generate an interrupt. The priority daisy chain is what that's called. The CTC is the highest priority. And if there is no CTC in there, nothing authorizes the SIO chip to ever generate an interrupt, which can be a problem. So these resistors here are optional. Rather, R10 is optional, I should say. R13 is required. R10 is optional if the CTC is present in the circuit. If you look at the schematic over here, there's a comment I wrote in here. It says populate R10 when the CTC is not present. Okay, otherwise it's optional. Okay, this is important that this signal here is high on the SIO if there is no CTC in the circuit. All right, so I added the R10 and so that the SIO can run without the chip in there. Okay. So let's look then at the individual tracks and the traces and stuff of what's going on in here. All right. Now, when I first laid this board out, I knew that I wanted a header over here, right? This 40-pin header. I wanted every single pin one at a time from the CPU to be pinned out into a header so that I could put clips and stuff on these really easily. Now, I have a special clip that I can use that clamps on the top of a DIP chip like a Z80, okay? But you may not have one. And if you're poking around with a little probe on all these little pins, you're looking up maybe at a meter or an oscilloscope or something like that, been there, your probe could slip and you could short two of these pins together and you got a problem. It's much easier using a header with a giant naked pin sticking out, especially if you have the little jumper wires with the little female like pin, like a single pin wire with a crimp on end that you can just push on these individual pins, and the other end you can put into a breadboard. Okay, that's exactly what I was thinking when I put that header on there. The other thing I was thinking was that, if and when I get around to writing the software for this, and if it all works, and yes, it does, I'm on Rev 3, even Rev 1 worked correctly. And the failure with Rev 1, as a side note, is I don't know how I managed it, but I put the wrong socket for this chip over here. I don't know if that's in the GitHub revision log, but it was very embarrassing and incredibly dumb. You only, you spend all the time working and designing a circuit only to put the wrong footprint down on one lousy part, and then, yeah, it works. I was able to jerry-rig it together to verify that it all worked. But, yeah, that was a bummer. So that got version 2, and I already talked about why I created version 3, because I want to add this header here to get rid of the CTC because I couldn't buy one. Anyway, the other thing I'm thinking is I want to make daughter cards for this. So that the first one I made was the flash programmer we'll talk about in some other video. What it does is it connects up to this connector here, and it tells the CPU to go into a standby mode. It requests control of the bus. The CPU steps aside, and the flash programmer can control this entire board. What it does is it generates signals to control the flash chip, and it writes new values in there. So that's how I've programmed my flash chip. That daughter board, as I designed it, if you order it from one of the popular proto shops, it's $2, all right, for 5 of them. Right? So that's as low as I could get the price. And if you order it in the same time you order your retro board, if you're going to order these yourself, you pay the extra $2, and you can then amortize it in the same shipping. I think it adds 50 cents or 10 cents to the shipping to get that thing added to your order if you order them all at once. So it increases the total cost of the circuit boards, just the boards, by $2 and I don't know, 10 cents or $2.50. I think that's a good deal. Otherwise, you're going to buy a $20 or a $50 flash programmer. Some of them cost like $800. No. All right, so yeah, this header is going to be our friend. Okay, this is how we're going to program the flash chip. What else do we notice about this? It's a 4-layer board. The inside layers, as I already mentioned, have power and ground on them. We'll take a closer look at that in a minute. The signal traces are all on the front and back. The front layer here is what we're looking at. That's the red one here. You'll notice on the front layer, all the tracks pretty much almost entirely run horizontally. Okay. The back of the board, which is in green, all these tracks run vertically. All right. When you have a 2-layer board like this with any density at all, you want to route your board like this. There's 2 reasons. One, you actually can't route it any other way. If you do something like run a track over here and then turn and go vertical, you've just blocked your ability to run anything else horizontal on the front layer. So then you start running the horizontals on the back layer. And then if anybody ever goes vertical on the back layer, you can't do it on either layer, okay? So it turns out you really want to say one direction on the front of the board and the orthogonal direction on the back of the board, right? Just so that it can be done. Even if you're doing this. Now, did I need to do this here? Probably not. And this is routed pretty poorly anyway. It actually goes down, turns around, come back. You know, this is, again, this sort of thing. Every time you look at a board, you're like, I probably want to clean this up, clean that up. And I might have moved this around if I didn't share this project with everybody. If I move it, I'm going to have to regenerate all the Gerbers and then verify they're all okay and upload them to GitHub and all that other stuff just because I moved one lousy VIA. All right? Don't do that unless you have to. I've noticed some other things I don't like. Like I said, the power distribution, I might tweak that and come up with a 3.1. Maybe I'll move that VIA at that time, all right? So what's my point? I move horizontally here. I go vertical on the back of the board. Period, okay? Do I need to do it here? No, obviously I could just have done this. And maybe I even should have, you know, when I'm cleaning the board up in the end. Yeah, okay, maybe. But while you're doing your work in here and you're evolving this design, like right up in here, you do run into problems, all right? Does this one need to go to the back of the board? No, this one could have gone around. But what if I made that choice here, right? I would have blocked my, you know, all these other stuff. You get into all these problems, okay? So that's why you do the horizontal vertical thing. The other reason you do horizontal and vertical is because of how the energy moves along these tracks. If you made a two-layer board. If you make a two-layer board and these all cross orthogonal to each other, like this track here, would not generate, you know, electromagnetic waves that would cause crosstalk and all these vertical green lines here. Okay? As long as you keep them on a 90-degree crossing of each other. All right? That's very handy. Now, this is a 4-layer board, so that doesn't really matter here because I have a ground plane in between. It shields everything anyway. But as a general rule, you need to do this just for practical routing reasons and for crosstalk and noise and stuff like that, okay? Now, it just so happens that if you have a ground plane inside here, what happens is it gives the return current somewhere to go other than in a giant loop, all right? You can go see, is it Dave Jones' channel, the EEVblog? Go look at his series on loop currents, okay? And he measures them, and he's got all kinds of really interesting equipment that measures magnetic fields and electric fields and noise and what happens when you radiate all that magnetic noise out of there and you violate your FCC. Well, you don't violate it. You end up unable to get an FCC rating for your board because it generates all this, you know, electromagnetic interference and disturbs Wi-Fi and radio and TV and stuff like that. And the reason that happens is because people create circuits where, you know, a signal that's running, you know, current through this wire over here to get to this chip has to have a return path somewhere. And if you send, you know, if you change a signal from like 0 to 1, it goes from ground to 5 volts. And all of a sudden there's this rush of electrons here. It causes this, you know, magnetic wave, electromagnetic wave to be radiated. And it turns out that the proportion of that radiation goes up based on how far it has to go for it to loop around and then go back to where it came from. Okay, so if this sends 5 volts to this pin, say over here, all right, and let's say ground is way over down here somewhere. In fact, maybe this is the ground pin on the chip. Okay, these are pins that connect to ground, whether that's the power ground or not, I don't know. But let's say the current has to flow through the chip and go to ground all the way over here. And let's say I don't have a ground plane in this design, but instead I have an explicit track that runs maybe down and around over here and back to this connector. then what I've created is a loop that goes over here, into this chip, through the chip, out there, down there, and back to ground down here. And it creates this giant circular loop in here, okay? When you do that, the area of that loop is proportional to how much electromagnetic energy goes all over the place, okay? That's bad. So if I turn on the polygon fills, what I've done here is I've done a couple of things. One, I fill the board with ground on the front and on the back. The green layer is the back here. The red layer is the front. So you can see all that red is grounded, all right? But even if I didn't do that, okay, if I turn off the front layer and I turn off the back layer and we only look at the inside layers, all right, so this is inside layer number 1. The yellow layer, as you can see here, is connected to the ground pin and the vias and these studs in the metal case and so on. So this is ground. It connects ground everywhere in the entire board. So if something wants to send a signal down a track that runs along here and into this pin, the return path is right underneath that track. You can't have a smaller return path, okay? So this is why these things generate a lot less noise if you have a ground plane. They also generate less noise because with the ground plane right next to that track, it adds a certain amount of capacitance. It's not always desirable, but it's just a couple of, not even, maybe 1 or 2 picofarads, if that. The tiny amount of capacitance causes the signal, when it goes from a 0 to a 1, or from a 1 down to a 0, the slew rate, we call that, the rate of change of the voltage on that signal is limited based on this parasitic capacitance and inductance in the copper tracks and stuff like that, okay? So we say it slows down the transition from a 0 to a 1, ever so slightly. And it is the rate of change that defines the like the magnitude of that interference, all right? So if it went from 0 to 1 instantaneously, it would require an enormous amount of energy to make that change in a very small amount of time. The longer it takes to go from one state to another, the less problem you're going to have with, instantaneous current draws and radiation and stuff like that, okay? So it's nice having a ground plane, okay, is the bottom line. This other one over here, inside layer number 2, the pink one, is the 5-volt plane, and this is what I was talking about a little while ago. And the inside plane looks like this. So the only way this is connected up to the 5 volts from the USBs around this hole here, and this hole here, and that hole there. All right? Now, what I probably should do, like I said earlier, is on the front layer here and on the back layer, I should probably just put a big fat track right along in there, right? And then up and around through here, this pin, and over to there. And when I'm done with this, maybe I'll do that, and eventually I'll release the 3.1, or maybe I'll wait until there's some more comments that I see below. Again, critique this thing. If I did something incredibly dumb, let me know. Don't just run off and hide. I guess there's YouTube standards. If you get really nasty, they'll get upset with you. So maybe use kind words to satisfy YouTube, but if I make a stupid mistake, let me know, all right? Like I said, the first time I did this, I put the wrong darn socket on here, and I couldn't even fit the chip into the thing. Oh, it was embarrassing. I hate that. If you can't laugh at yourself, you shouldn't laugh at anybody, I guess, is the takeaway on that. But, oh, geez, was that stupid. Anyway, okay, so moving along. This is, again, the motivation why I did what I did. The biggest impact, I think I mentioned this before in another video, is that when I made the board, I made sure it was 100 millimeters by 100 millimeters or smaller. I just said, I drew the outline of the board right there and said, well, no matter what I do, I need to fit it in here. And by doing that, it cuts the engineering fees down. You can use the special prototype rate from some PC board houses And in the case of where I ordered these, I get no sponsorship on here. I love my Patreons, and I like the ad revenue I get. I shut off mid-rolls, by the way. I can't stand those. In the new videos, I don't turn on the mid-rolls anymore. I'm like, I can't take it. But please tolerate whatever advertising rolls in the beginning and the end, because it helps support the channel, as well as my Patreons. Again, thank you as well. But my mind wanders, and in terms of money, I apologize. The place I order my boards from for this particular project was JLC PCB. They seem to sponsor everybody on the planet. I never reached out to them to sponsor my channel because I don't want to hear about them in all of my own videos as well. I mention them because I know the rates, okay? So if you order your board from JLC PCB, they charge you, if this is 1 millimeter bigger, it'll be like $18 more for the board, okay, because of what they call an engineering fee, okay? So if you keep it 100 millimeter square or smaller, you go to PCB Way or JLC PCB. I order from both of those from time to time for these boards. The prices are, in my opinion, low enough that I'm surprised that you can even make it for that. So I'm very happy with their services. And I'm happier when it's only, $2 for the two-sided board that I use for the FPGA or the Flash programmer. And this board here at 4 layers turns out it's $8. Okay, so it will cost you $10 all in to order the retro board and the Flash programmer board, and then you got to pay shipping, which is about $18 or $19 if you want to get it in 5 days from DHL, which to me just seems insanely cheap. In fact, I think I misquoted the shipping price. It's less than that. Including shipping, all the boards all in cost me less than $25 US. I mean, wow, mind blown, okay? Just an outstandingly awesome deal, all right? And why? Because the board is only 100 millimeters square. Don't go bigger than that, or else you'll be out a whopping $18 more, okay? Okay, so you know about the big slugs, you know about the pin 1. I warned you that this resistor network flips down and the one up here flips up, okay? And as I said, now that we're looking at the board, you see how this weaving pattern comes in here? The address lines, the data lines, all kind of go back and forth and weave through here. This is why these resistor networks don't necessarily go in order when you look at the schematic. You see 12, 13, 14, 15, and then all of a sudden you see 5, and then for the address lines, and then D4 and D3. Well, why did I choose this random wonky order? Why? Because that's where the pin is that I want to hook up to it, right? The Z80 has D4 right there. I don't want to have to route tracks all over the place in here. Giant tangled spaghetti mole mess. Only so that this schematic over here looks nice, all right? What you're looking at there is this resistor network right here, RN4. Why does it go 12, 13, 14, 15, 5, blah, 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 blah? Why? Because that's the physical location of the pins on the Z80 over here, all right? This is the optimum way to put these resistor networks in the board. Okay, so that's true down here as well. Some of the data lines, you got the interrupt bit and stuff like that. That's why they're wonky. Now, as I mentioned before, one of the resistors networks goes up, the other one goes down. Well, if this here is the 5 volt, this is where the pull-up voltage is, right? And this wire goes inside the resistor network, right? It runs along here, and all the little resistors inside connect individually to these pins over here. If you turn this around the other way, so the board is orderly, there would not be a resistor pad here. There'd be the 5 volt pad here. This one would have to go down here and then come back up. Is that the end of the world? No, not really. But as it is right now, this weaving pattern is cleaner and there's less stuff running all over my board. That's why this resistor network is in upside down. And now that I've carried on about it for 10 minutes of your life, hopefully you'll remember to put it in the right way when you put your circuit board together, okay? This slug may not be super duper visible because it's going to be partly obscured because the silkscreen won't print over these pads here, right? But it'll still be there. If we go back to the 3D view, Where is it? It's over here. You can still see it hiding in there, okay? But visually, it may be a little bit obscured, and you could get disoriented. Make sure you put this in the right way, okay? I also did you the favor, and myself, I should say. I did this for myself more than anybody else. I'm greedy. I want it. I put the sizes of the resistors on the silk screen. Okay, it took a while to go back and do all this and update them all, make sure they're all the same, they all are correct, and double check every little one. It's the worst thing to put 2.7 on the silk screen where you meant to put 4.7. Don't lie to me. That makes it even worse, right? So I went back and double, super, triple checked all this stuff. So I hope it's still right. If it's not, let me know in the comments below. So when you're putting the board together, you know what resistors to put in here. You don't have to go look up, well, it's R3 again. Oh, that's supposed to be a 2.7, and you put it in there, okay? I try to put these right on the board. You can't do this on a surface mount board because the parts are way too tiny. But if you're going to put these gigantic parts on a board, there's plenty of room to put the little sizes on here, okay? So, yeah, that's what I did there to help you put the board together. So you, aka me, doesn't put the wrong lousy part on there. The LEDs, when you put these in, remember that the short pin on the LED is the ground pin, the pin that's connected to the lower voltage. All right. Now, both of these LEDs have the same orientation. The short pin goes on the square hole. Okay. Spoiler alert. It won't light if you put it in backwards. Okay. Now, what I do is, since day one, I was always good at putting LEDs in backwards, and then you don't have to unsolder it, take it out, then you wreck it, and you throw it away, put another one in the hole if you put it in backwards, okay? When you put those LEDs in here, what you can do is put these resistors in first, okay? Because it doesn't matter. These can go in backwards. Resistors don't matter. I like to put them in when I make my PC board so that all the stripes go the same way and it's orderly, okay? Because it looks nice, you know, why not? A little craftsmanship there. Put in your 680 ohm resistors is my point, okay? Decide which way you're going to make them all go, make them all the same. And then you can put the USB connector on here, hook up the power. And you can then take the LED and you can poke it in the hole by hand, and it'll make contact, right? You could bend it a little bit left and right. It doesn't require much, as long as the two leads make contact, and make sure the power LED turns on, okay? If it's on, it's in right, all right? The disc LED will only go on when the CPU sets the port to light up the light, so this one won't go on by default if you just simply... Arguably, you should put the regulator and the SD card on first if you do it at all. When you're done with that, put on the USB connector and these resistors, and then put the power LED in here. And while you're at it, put this one in, because they'll both go in the same orientation, is my point. When you poke the LED in here, you'll figure out which way it goes if you don't know. Especially if you already cut the leads off or something, where you got an LED that doesn't have a flat on it. You can sort of tell by looking at the inside. You can see the metal parts inside, and you can figure out which one's negative. But you can't beat just stuffing it in the hole and say, did it light up? It's okay to put it in backwards. You're not going to blow the thing up. If it doesn't light, turn it around, put it in the other way. Okay, you figured it out, shove it in the hole and solder it in. Now, I put the power LEDs in my circuits right away, and I think I mentioned this in another video, because in days gone by, I didn't always have a power LED on my projects, and once in a blue moon, I'd start poking around on a board when the power's on without knowing. So these days, I always put a power LED on there, and I solder it in first before I do or test any other part of my board. Because when you're doing work, and then you power it up and test it, and you do some more work and so on, as when I run into the problem where I forget to shut the power off, and the next thing I know, I've destroyed something. So, trust me, put the power LED in first if you're going to build your board incrementally. And if you've designed this yourself, you probably do want to build it incrementally. Now, I know this board works, so if you really wanted to, and you had a board and you had all the parts, you could just solder in all the parts, turn it on, and use it, okay? Now, that may not be a good idea, even though I know it works, Okay, if I was to build one of these, that's what I would do. But if you are just getting started in this sort of thing, and you just solder in every one of the parts and then fire it up, you may not notice a solder bridge or something else. You could have made a mistake. Okay, you're still probably better off incrementally assembling one section of the board at a time and testing it as you go than you are to say, let's put in every single thing and cross our fingers and hope it works. Okay, if you nothing works on the first try, and it makes it really difficult to figure out what went wrong if the answer is it could be anything. All right, that just, no, don't do that. That's a waste of time. If you take another route and do this incrementally as you go, you're way better off. Like testing the voltage regulators before you hook up any chips would be a good idea, and make sure the power and the voltage is not higher than it's supposed to be and stuff like that. Because you're going to burn up all the parts if you did it wrong. You put something in backwards or a diode in backwards or something like that. The next thing you know, everything's busted. And that's really depressing and very frustrating. And that's when you, in my case, I teach the neighbor's kids new words. Bellowing out the window in the old basement shop. You don't want to be that guy, okay? Anyway, so there's a walkthrough of the circuit board. I hope this has been enlightening in some way. Otherwise, who knows? It's a little free associating on how to make these things. Why I did what I did. Any questions, feel free to throw them in the comments below on YouTube. Thanks for watching. We'll see you next time.